What we're going to look at next are compressors, and this takes a little while longer than the thermostatic expansion valve. And so what we're looking at here are reciprocating compressors, and I refer you to figure 16.8, which shows a two-stage reciprocating compressor with an intercooler in between. And so what we have is that, so when you look at this, one of the things I'd like you to look at is that the valves are flexible discs. So what happens is the pressure causes the disc to deflect. So I have something like this. So the movement is caused by this, so it isn't like a valve that we tend to think of as in an internal combustion engine where there's a valve with a valve head and there's a valve seat and all that, so it's different. And what happens here with this two-stage compressor is that you have the first stage, and this is where the intake is. It then discharges through an intercooler and goes into a second stage. And then this is your discharge. So when you look at the diagram, you'll see that the first stage cylinder is bigger because the air is at a lower pressure. The second stage cylinder is smaller because the pressure is higher and the air is more compact. And this is the intercooler that cools it down. And we'll look at the intercooler in just a second. But this is just to give you an idea that when you look at this figure, what you're really looking at, what's going on. So the first thing we'll do are compressors without clearance, then we'll add clearance and see what happens in terms of the compressor performance. So compressors without clearance. And in this case, if I had a PV diagram, let this be 0. So 1 is at bottom dead center, so here we have this BDC, and so it's at bottom dead center, and now it's going to compress. It's going to compress the gas, and so I could have a compression like this to state 2, state 2, and this would be PV to the end. And so this is our polytropic or isentropic if n is equal to k, etc. And so if I have an isothermal compression, it'd be something like this. PV is equal to a constant, so that's your isothermal. And so we have, typically we talk about adiabatic compression or isothermal compression in terms of how we're rating them. And we have 0 to 1 as our intake. 1 to 2 is compression. 2 to 3, oops, this is 2, and here's 3. 2 to 3 is discharge. And so what happens is we're assuming that the piston goes all the way and all the air or all the substance in here disappears, and then it drops right back down again and we start the intake. So that's what it looks like. And so if I define the work, 0 to 1, it's equal to the integral of P dV is equal to P1 times V1 minus P0 is equal to P1 V1. So V0 is 0, so we have that. W12 is equal to P2 V2 minus P1 V1 over 1 minus N. So we have that for your polytropic compression. And W223 is equal to constant pressure V3 minus V2, which is going to be equal minus P2 V2. Because V3 is 0. And so the work from 3 to 0 is 0. And so I add, if I sum all the works, we'll get that this is n over n minus 1 times P1 V1 minus P2 V2. So this provides us with the work for the compressor. And what we're going to do now is do some manipulation of this stuff and get this in a form that we've seen before. So P2 V2 over P1 V1 is equal to P2 over P1 to the n minus 1 over n. And so the work for a cycle is equal to n over n minus 1 times P1 V1 times 1 minus P2 minus P1 over n minus 1 over n. And this will look familiar to you from chapter 6. So it looks familiar from chapter 6. If I have a volume flow rate, I'll rewrite it. So we have W dot cycles. So now we have a volume flow rate is n over n minus 1 times P1 V1 dot times 1 minus P2 over P1 to the n minus 1 over n. So I have that. And from the ideal gas law, P1 V1 dot is equal to m dot R T1. So I can, as we did in chapter 6, I can use the mass flow rate here, I can use the volume flow rate. As I indicated before, the compressors depend on this volume flow rate, so we're going to look at that in just a little while. So this is for the polytropic case, for which we could use n equal k for reversible adiabatic. If I looked at the isothermal case, which I won't go through the whole thing all over again, so for isothermal, work of the cycle is equal to minus P1 V1 times the log of P2 over P1. And we can, so that was where the compression was isothermal rather than it was polytropic. So this is for a compressor with no clearance, and now let's look at what happens when we have compressors with clearance, which is what all compressors have. And we'll draw this on a PV diagram. So we're going to let these both be PV to the end. I mean, so what happens in the text, and when you read that, you'll see that I could let this could be a different polytropic process than this, but for simplicity, we can let them both be the same. This is the intake, so this is intake. This is your clearance volume. So that's V3. And obviously, this is your piston displacement. So we have your piston displacement as it moves between top and bottom dead center. And so the percent clearance C is equal to V3 over the displacement volume. So one of the things that we talked about in reciprocating devices is the percent clearance. So the percent clearance C is that. And now what happens is we want to take this. So if I look at this equation, I see this is the volume flow rate. The volume flow rate here, this is your intake volume. And so what happens when I have a compressor with clearance is that there's a vapor, either for a refrigerant, a vapor, or gas, or air compressor. And what happens is the piston has to move back. So I have my piston. It has a gas in here, and this has to move back to 4 until the pressure gets low enough for it to pull air in at the intake volume and at the intake pressure. So depending on how high this pressure is, depends on how long this intake is. So if I rewrite these equations based on the compressor with clearance, we're basically changing V1 to V1 minus V4. And then I can do the same thing for volume flow rate. And this is m dot RT1. So we have that. And now, so it's the same idea. It's just, this is the volume flow rate we have to compress, or this is m dot from the ideal gas flow. So we have that. We have something called volumetric efficiency, which measures how effective the intake volume occurs. So let's look at that. It's important for reciprocating devices. So with volumetric efficiency, A to sub V is equal to V1 minus V4, the actual intake volume over the piston displacement. And so V1 is equal to V sub PD plus C times V sub PD. And V4 is equal to V3 times P3 over P4 to the 1 minus N. These are these polytropic relationships. So V4 is equal to C, V sub PD times this pressure thing. And we'll do it P2 over P1. So I'll switch from 4. Pressures 4 and 1 and 2 and 3 are the same. And so I come up with an expression that the volumetric efficiency is 1 plus C minus C times P2 over P1 to the 1 over N. So now let's say that N is, so if I know C, I basically just substitute in. If I know C is 5%, I put in 0.05, etc., and I know the pressures, I can find the volumetric efficiency. Knowing the volumetric efficiency, then this, I find V1 minus V4. So, and that will change as a function of P2. So as P2 changes, the volumetric efficiency changes, and the amount of air brought in changes. So let's say N is 1.35, P1 is equal to 14.7 psia. So one of the things that happens if the pressure P2 is high enough, at some point the volumetric efficiency will be 0. So the mass of air trapped at top dead center expands all the way down, and there's no intake volume that occurs. And so let's solve and see what that is for this case where we have this information. So I have 0, so I want to have 0 is equal to 1.05 minus 0.05 times P2 over 14.7 to the 1 over 1.35. And so I have P2 over P1. I'll do all the math steps P2 over 14.7 to the 0.7407 is equal to 21. And so if I take the log, now I have to take the log of both sides and do all that sort of stuff. So I have 0.7407 times the log of P2 over 14.7 is equal to the log of 21 is equal to 3.044. What happens is a lot of you are not as familiar with logarithms as you'd like to be. And so I have then that the log of P2 over 14.7 is equal to 4.11. And if I solve for this, I'll get that P2 is equal to 896 psi. And so that tells me when the pressure is that, eta sub b will be 0. And I can check on that. I can substitute that back in this expression. So I did that just so you'd see that it works. So eta sub b is 1.05 minus 0.05 times 896 over 14.7 to the 1 over 1.35, and it's equal to 0. So if you do all the math, it's equal to 0. So now, let's look at the prior example. So the prior example that we did with R12 in the refrigeration area, we had that the volume flow rate at the compressor inlet was 221.1 cubic feet per minute. So prior example, V dot is equal to 221.1 cubic feet per minute. And we had that P1 was 15.2 psia, P2 was 132 psia, K is 1.129 for R12. Let's say as well that there are 4 cylinders. And we have L is equal to D for the 4 cylinders, and we'll say they run at 200 RPM. What happens in refrigeration compressors is that you tend to have, I'd have a cylinder here, a cylinder here, a cylinder here, a cylinder here, and then this is your crankshaft, and we have them all connected. And so I'd have four cylinders, and then basically what happens when we in refrigeration, as the load goes down, there are ways to decommission each cylinder. So basically what happens is you pick up the valves so they no longer work. So as the mass flow rate decreases because your cooling load decreases for your compressor, what we're doing is you unload your compressor. And it also means when you start up again, you're starting up with only 1 piston as the load rather than 4 pistons as the load. So it's a nice design, and the text talks about the unloading of the valves for this. But now, back to this problem. So anyway, we have 4 cylinders, 200 RPM, and all that sort of stuff. And we have what K is for this, so we can use the equations that we just developed to see what L over D is. And so we want to find that out. So I want to find that out. So now I use this, and since this is the volume flow rate, I can use the volumetric efficiency to find out what the piston displacement has to be. So A S B is equal to 1.05 minus 0.05 times P2, 132, over P1, 15.2, over 1 over 1.129, which is equal to 0.711. So it's 71.1%, and so V sub dot PD is equal to 221.1 over 0.711 is equal to 311 cubic feet per minute. And so now let's find it per cycle. So we take 311 cubic feet per minute, divide by 200 cycles per minute, and we'll get that this is 1.555 cubic feet per cycle. And this is pi over 4 d squared L times 4 cylinders. So this is pi d cubed. So I can solve for d, and d is equal to 0.791 feet is equal to 9.5 inches. And obviously if I had a faster RPM, then I would, and I just picked 200 for this example, so we would have 4 pistons, and this would give the bore and stroke of that amount. And now let's look at some compressor performance factors. So this is how I can size the compressor knowing information like this, my volumetric efficiency, and it gives me the ability to size how big the compressor should be. So compressor performance factors. And so we have a compression efficiency. And eta sub Cn is the theoretical work over the indicated work. So the theoretical work is either going to be your isentropic or isothermal. So we know what that is. So you know how to calculate that. We've been doing that. In the indicated work, is the work that the gas indicates was done to it. We also have so anyway, we have this compression efficiency. I don't tend to do isothermal that much in this chapter, so we'll have the isentropic, and then we would be measuring the indicated work, and we'll go through and see how this plays out.